Hi, I'm Nathan Schweitzner, and this is a summary presentation of our International Pipeline Conference paper number 9589, titled An Approach to Establishing Manufacturing Process and Vintage of Line Pipe Using In-Situ Non-Destructive Examination and Historical Manufacturing Data. My co-authors are Peter Valou, Mike Rosenfeld, Troy Rovella, and John Gibbs. We especially appreciate PG&E for sponsoring this effort. This talk will start off with some aspects of integrity management and the PHMSA mega rule that motivate us to dig deeper in our understanding of line pipe vintage and manufacturing processes. Then we'll cover some of the relevant aspects of the evolution of steel and line pipe manufacturing. Then we'll look at the historical data and non-destructive evaluation technologies that enable vintage estimation. Then we'll talk about the concept of the methodology, which is basically to align the NDE data with the historical data. We'll touch on a couple case studies and finally make some concluding remarks. So let's get started with the integrity management motivations. For operators who have older steel line pipe assets, there's a greater possibility of inadequate documentation. So operators might want to conduct non-destructive testing to improve their documentation. Simple tests such as hardness and wall thickness and outside diameter testing provide some information helpful to operations, but inadequate for integrity management. The next advancement is data collection for compositions such as carbon, manganese, and sulfur content, and so on, and also for microstructure and strength estimation. So these data provide additional useful information, but what this talk is all about is looking for trends in the historical data and mapping the NDE data to those historical trends to try to estimate vintage and identify the manufacturing process to optimize integrity management. So next, let's take a look at additional ways that the US federal rules drive our interest in identifying line pipe vintage and manufacturing. One driver for vintage estimation is population creation. If operators want to segment their assets into populations for the purpose of integrity management, the US federal rules require them to use grade, manufacturing process, and vintage to define those populations. So if the documentation is inadequate or incomplete, then some type of process using non-destructive or destructive evaluation needs to be applied to be able to establish those details about the population. Secondly, operators must identify the toughness of their vintage assets. They're able to use a Sharpie V-notch toughness value from comparable pipe as long as those are proven to be from the same vintage and the same steel and pipe manufacturer. So, for assets in the field that are vintage and don't have toughness data, there's a need to be able to confirm the vintage and manufacturing process for those assets so that available Sharpie toughness data can be used to corroborate those assets in the field. The main point is that PHMSA's mega rule is driving the development of new methods to estimate vintage and identify information about the manufacturing process. So now that we know that we need to identify vintage in manufacturing, where do we start? In the next slide, we're going to start a brief review of how steel and line pipe manufacturing has evolved over the years. We'll explore some of the major evolutions of steel making and line pipe making that have been driven by an increased need for safety and reliability, by improvements in technology, by economics, and by regulations. Firstly, for steel making in terms of refining, there's been a transition from the vintage processes of Bessemer and open hearth steel making to basic oxygen and electric arc furnace steel making. Those transitions show up in some aspects of the steel composition and cleanliness. Another transition that will show up in some aspects of the composition and cleanliness and possibly the microstructure is the transition from ingot casting to continuous casting for line pipe steels. Then in terms of rolling, which shows up most pronouncedly in the microstructure, there's been the advent of controlled rolling and accelerated cooling processes. And finally, definitely showing up in the composition are technology changes around the strengthening mechanisms from historic to modern processes that use alloying for strength and now microalloying. There have also been a variety of transitions in pipe making processes. We don't have time to go into depth about all the different processes and when they started and when they finished. But if you have data about the seamed or seamless nature of your assets, that will definitely help with the vintage confirmation. So the key takeaway from our time travel through line pipe manufacturing processes is that steelmaking and line pipe making have evolved over time, and some of those changes can relate to failure mechanisms and asset integrity. So the knowledge of those manufacturing processes and vintage of our assets is important for integrity management, and it would be valuable if we'd be able to distinguish or deconvolute our vintage assets based on the data that we can collect about things like composition, microstructure, and mechanical properties. So starting with the next slide, that idea forms the basis for the concept of the methodology. What we're proposing is that if you have a database with enough data to show precise enough historical trends and changes in the composition and strength over time, then you can also collect accurate enough non-destructive data for strength, composition, and microstructure. Then you can put that data together with the historical database and map the NDE data onto the historical trends, and then be able to, with some amount of precision, identify a vintage and use that together with the microstructure to get some idea about the manufacturing process. So we're going to call these our enablers. Number one, a database of historical trends. Number two, the NDE estimate for strength. Third, composition. And fourthly, microstructural replication. Firstly, in terms of enablers, our database of historical line pipe test results came from about 1,200 pipe segments from PG&E and industry data sets from a wide variety of pipe sizes. We were able to identify interesting trends in the data in the strength and composition by plotting the data over time. For brevity, we're only going to discuss the historical trends for yield strength, manganese, and sulfur. But if you want the full breadth of our study with the additional plots, take a look at our IPC 2020 paper 9589. So how are these plots created? Let's start with the example for yield strength. Firstly, all the data in the database for our line pipe steels were binned by decade of manufacture, plus or minus 1 decade for smoothing purposes. Then these data were plotted against decade of manufacture. Here's an example of average yield strength versus vintage to get an idea of the appearance of the trend. In this case, our data show that strengths at the turn of this 20th century were low and gradually increased, which makes sense as there were technology-driven improvements in the strength of steel over time for line pipe. Now we also wanted to get an idea of how the spread in the data changed over time. So the single standard deviation and the 2 standard deviation were added to the mean data and plotted as well. And the results here show, as you would expect, that the spread of data increased over time. And the distribution started out with a very narrow spread and gradually widened. And for yield strength, this widening was because additional grades of higher strength steel were introduced by API 5L. But the lower grades were still being produced as well. So we didn't think it made too much sense to add a lower limit to the distributions for yield strength plot, because grade B has been relatively static since the beginning of API 5L. So the lower bound could be assumed to be a straight line at low strength. Now one way that this plot could be used was if you walk up to an unknown pipe and do your NDE and discover that the pipe is an estimated yield strength of about 75 KSI, you can be relatively certain that this is a more modern steel and not one of these vintage steels that would tend to have a lower yield strength. But we wouldn't make conclusions based on one type of data if we have other data available, so it's highly preferable to use the composition data as well. So we'll demonstrate that with the process using manganese and sulfur now. Here's the historical trend for manganese. Here we have a mean starting around 0.5 weight% manganese, about 1900, and increasing to about 1.25 weight% manganese in modern day steel. So we see an increase in the spread as well for manganese over time. So these trends are because manganese has proven to be an important addition for stronger, tougher steels. The average in manganese has about doubled in the past 80 years. So for manganese, it made sense to include a lower bound because there's typically a target for steel producers and line pipe producers. The last historical trend that we're going to show in this presentation is that for sulfur. Sulfur content follows a log normal distribution because it's been recognized as a tramp element for a long time. And so the desire of steelmakers for line pipe has been essentially to eliminate sulfur. you can see a dramatic decrease in sulfur over time, which makes it very useful for aligning with the NDE data. Historically, sulfur content was well above 0.01 weight percent, as you can see at the bottom of the plot. But for modern day steel, sulfur contents are well below 0.01 weight percent. Additionally, the distribution of sulfur has stayed fairly tight through the years, indicating that the entire line pipe making industry adopted sulfur reduction technologies somewhat uniformly as new technologies became available. So thanks to this tight distribution, the high sulfur steels from today are still lower in sulfur than the low sulfur steels from 100 years ago. Again, this dramatic decrease in sulfur content makes sulfur very useful for vintage estimation. So now that we've covered how historical strength and composition trends were our initial enabler of vintage suggestion, let's look at the NDE data that we need. PG&E has validated an NDE strength test called instrumented indentation testing, which uses precise, iterative load versus depth measurements to estimate yield and tensile strength. IIT has been validated using comparisons with laboratory tensile tests to adequately produce an estimate for yield strength. And some of the PG&E documentation can be found in the publications shown at the bottom of this slide. So if you'd like to take a look at some of these publications, please email the address you'll find in the last slide. For composition, PG&E has tested a variety of NDE compositional detection techniques and found several technologies quite capable of producing accurate results, such as what you see here for the element manganese. So this example validation plot shows that the NDE composition method of filings collection and measurement of manganese correlated very well with the laboratory measurements. Similar validation plots have been made for a number of important elements and published by PG&E in the publications shown at the bottom of this slide. The final enabling technology for NDE that we're going to discuss in this talk is microstructural replication. A clear view of the microstructure is the most important tool that we have for identifying the manufacturing process. I'm going to show three microstructures on this slide that represent three very different manufacturing processes. And important features in the microstructure are, one, the grain size, which is the size of these light areas called ferrite, and two, the fraction of these dark areas or lamellar areas called pearlite, and three, the shape of these areas called morphology. So here we have a normalized microstructure which is characteristic of a lot of vintage steels, and it's evident of older or low-grade pipeline steels with these large ferrite grains and large amounts of this dark phase called pearlite. Now in the middle, we have a microstructure produced by a more modern process, the quenching and tempering process for steelmaking, and we see small jagged grains and almost no dark phase. And on the right, we have a second microstructure produced by a relatively modern process called thermomechanical control processing for steelmaking, and we see fine ferrite grains and only a small amount of dark phase. So these are just some of the important differences that can be observed between microstructures for different manufacturing processes. Now next, let's take a look at our two case studies for vintage estimation. The first of our two case studies is for a line pipe that was reportedly installed in 1952, and the NDE data provided an estimate of about 43 KSI yield strength, a manganese content of 0.5 weight percent, sulfur of 0.026 weight percent, and the microstructural replica shown here. The second case study was reportedly installed in 1951, but the NDE data provided an estimate of 75 KSI yield strength, manganese content of 1.28 weight percent, sulfur of 0.005 weight percent, and this microstructural replica. Let's take a look at how our NDE data for yield strength mapped to the historical trends that we built. For case study 1, we see that the yield strength is slightly below the mean line. And for case study 2, we got a yield strength that is 2 standard deviations above the mean line. So that tells us that case study 1 is low but reasonable for the 1950s, but case study 2 is a yield strength that is quite high for 1950s line pipe. Next, let's look at our composition data starting with manganese. We see for case study 1 for manganese that the value is low but reasonable, and case study 2, the value for manganese again is on the 2 standard deviation line. So it's quite high for the 1950s. Finally, let's look at sulfur. For case study 1, the filings estimate for sulfur is very close to the mean that would be expected for 1950, but for case study 2, the estimate for sulfur is way below the 2 standard deviation line. So this low sulfur content is very unlikely based on the poor sulfur removing capabilities prior to the 1990s. Let's wrap up by examining the microstructure. For case study 1, we see relatively large ferrite grains and a good amount of this dark phase perlite with these lines called lamella that indicate slow cooling. For case study 2, we see much finer ferrite grains and dark phase with no discernible lamella. So these provide evidence of manufacturing much later than the 1950s. So now that we've looked at the yield strength, manganese, sulfur, and the microstructure, our next step is to suggest a vintage for case study 2. We've confirmed that case study 1 appears to be representative of a 1950s steel, but case study 2 appears to be more modern. So more composition data was considered in the paper associated with the presentation, but we can't cover all right now. So to suggest a vintage for case study 2, the data were prioritized and aligned with the most likely vintage from the historical trends that also found agreement with the microstructural observations. And this method was used to suggest an updated vintage of the year 2000 for case study 2. And here you see that the suggestion of the year 2000 rather than 1951 for the steel line pipe from case study 2 aligns much better with the historical data. On the left we have yield strength. In the middle we have manganese. And on the right we have sulfur content. And you see that the realignment to the year 2000 brought the data much closer to the mean line and the expectation for that vintage. In conclusion, what we've done here is to propose a new method to confirm or suggest a vintage for line pipe steel where it's not known. Now this method relies firstly on an extensive database of strength and composition data, and secondly on accurate NDE data for strength and composition and microstructure. Some future work for PG&E is going to include expanding the historical database for strength and composition and microstructure, and also introduction of algorithms to aid with the vintage estimation and improve the certainty of this process. If you have any comments, I would love to hear them, or your questions, please send them to nsweitzner@rsips.com. Thank you.